Top-down recursion, a new way of thinking. Specifically, when we go top-down, we get to mentally kick the problem down the road. We can free our mind from some of the nitty-gritty details we normally have to think about when going bottom up. So we avoid the details or hard uh, way of solving problem from bottom up when we start from top to down. So this is the essence of recursion. We don't need to worry about what it does in that nested subdirectory. We just need to properly integrate it or properly create the function for the function to uh, iterate through the nested loops. Kind of like how programming works nowadays. You don't need to create or to understand the nitty-gritty details from the ground. You just need to know that you did the right thing from the top or on the system design, because you're just gonna use this AI to deal with those gritty details, which are not, I mean, it's not, we're not good at it for that details, because most of that is repetitive, and we just need to understand the big picture so that we could understand those nitty gritty. So this is kind of like the essence of the top-down recursion. To see what I mean, let's take another example at the keyline from our top-down factorial implementation. So return, so this is the code that we use in factorial. Return number times factorial number minus 1. This line of code makes its calculation based on factorial number minus 1. When we write this line of code, do we have to understand how the factorial function it's calling works? Technically, we don't. Whenever we write code that calls another function, we assume that the function will return the correct value without necessarily understanding how its internal works. Here as well, when we calculate our answers based on calling the factorial function, we don't need to understand how the factorial function works. We can just expect it to return the correct result. Of course, the weird part is that we're the ones writing the factorial function itself. But that's what is so great about top-down thinking in a way. We can solve the problem without even knowing how to solve the problem. When we write in recursive to implement a top-down strategy, we get to relax our brains a little bit. We can even choose to ignore the details of how the calculation actually works. So it's kind of like in design principles by about Facebook is that we're like computers. So once we write this function, or like the CPU before, there's a lot of idle time. So because those idle times actually could be put to work, while it's idle. It's kind of like that in here, because once we write the code, so it's like when the CPU returned the function before, it just stays idle instead of preparing for the next prompt or search of the user, or doing something in the background that will help the user cognitively. So it's kind of like this in a way. So when we write in recursive to implement top-down strategy, we get to relax our brains a little bit, so we can use that to create or to minimize the cognitive load for further functions or tasks that we need to do to create our app. So we can even choose to ignore the details of how the calculation actually works. We get to say, let's just rely on the sub-problem to deal with the details. The top-down thought process. If you haven't done a lot of top-down recursion before, it takes time and practice to learn to think in this way. However, I found that when tackling a top-down problem, it helps to think the following three thoughts. A. Imagine the functions you're writing has already been implemented by someone else. Identify the problem, sub-problem of the problem. So it's like the sub-problem category that we use to write or use as a way for us to create or to write recursive function. See what happens when you call the function on the sub-problem and go from there. So it's kind of like starting from the base case of the sub-problem as a way for writing recursive function. This is also another detailed way of looking at that. Now let's say we're calculating the array sum. Let's identify the sub-problem. This can be more of an art than a science, but practice will help you get better at this. In our case, another thing is that though people think of writing code as purely science, it's actually not. This can be more of an art than a science, especially for writing recursive function, but practice will help you get better at this. In our case, we can say that sub-problem is the array 2, 3, 4, 5. That is all the numbers from the array, save the first one. So this the array that we're gonna is the subset of the whole problem. So our base case is obviously 1. So finally, let's see what happens when we apply the sum function to our sub-problem, which is 2, 3, 4, 5. If the sum function already works and the sub-problem is 2, 3, 4, 5, what happens when we call the sum 2, 3, 4, 5? Well, we'll get the sum of 2 plus 3 plus 4 plus 5, which is 14. So to solve our problem of finding the sum of 1, 2, 3, 4, 5, then we can just add the first number 1 to the result of sum 2, 3, 4, 5. So it's like the base case that we've defined before. In pseudocode, we'd write something like this: return array with the index 0 because it's the number 1 plus sum the remainder of the array. In Ruby, we can write this as return array index 0 plus sum array open parenthesis 1 array that length minus 1. So essentially putting the 1 as first parameter of the array and then comma array that length minus 1. So in many language, the syntax array xy returns an array from index x through index y. So in many language, the syntax array xy will return an array from index x through index y. Now, believe it or not, we're done. Save for the base case, which we'll get to in a moment. Our sum function can be written as, so it's in Ruby as well, def sum function with a parameter of only 1, which is array. Return array index 0 plus array start with 1 comma array that length minus 1 and then end. So the last thing we'll need to do is handle the base case. That is if each subproblem recursively calls its own subproblem. So again, we're trying to call this function inside our function, which what essentially recursively calls is about, will eventually reach the subproblem of sum5. So the function will eventually try to add the 5 to the remainder of the array, but there are no other elements in the array. To deal with this, we can add the base case. So here, def sum array again with the 1 parameter, base case, only 1 element in the array. So these are how we create the base case. Take note: return array index 0 if array that length equals to 1. So it's just in one line. Then we return the previous code, which is return array index 0 plus sum array with 1 comma array that length minus 1 parameter and then end. So let's try another example, string reversal for the string ABCDE. Let's assume the problem is BCDE. So that's the subproblem again. This subproblem is the same as the original string minus its first character. Next, let's imagine that someone did us the great favor of implementing the reverse function for us. How nice of them. Now, if the reverse function is available for our use and our subproblem is BCDE, that means we can already call reverse BCDE, which would return EDCB. So, since we already have a functions for the subproblem BCDE, we know that we could return the reversal of that string, which in this case EDCB. Once we can do that, dealing with A is a piece of cake. We just need to throw into the end of the string. So we can write with def reverse and then one parameter of string again. Sorry, array before the parameter is array, now it's string, but it's the same as it has one parameter. Now return reverse string, then one again with parameter 1 comma string that length -1 plus string index 0, kind of like the return array index 0 plus some array. In this case, it's just the reverse function. So we call the reverse inside our reverse function. So our computation is simply the result of calling the reverse on the subproblem and then adding the first character to the end. So our computation is simply the result of calling the reverse on the subproblem. So we call the reverse of the subproblem and then adding the first character to the end. Once again, save for the base case, we are done. I know it's crazy magical. The base case occurs when the string has one character. So we can add the following of code to handle it. So one of the characteristics we notice or observe throughout this discussion is that the base case, usually the first character or first number, right? And then we divide it by the other with a recursive function itself or the subproblem from that second next to base case until the end, and essentially we're calculating the all the numbers accounting for that problem, so all the strings accounting for that problem. So our computation is simply the result of calling the reverse on the subproblem and then adding the first character to the end. Once again, save for the base case, we are done. So here we define it's the same code, def reverse parameter string, but with the base case. Again, it's still Ruby base case string with just one character. So how do we do that? Return string index 0 if string dot length equal 1. So if string that length. So in the previous case, what we did is if array that length equals 1. So it's the same pattern. Another example, which is last, is a function called count underscore x that returns the number of x in a given string. So lo and behold, we're still gonna use the base case and then a subproblem to write a recursive function for this. If our function is past the string ax, bx, cxd, it returns 3 since there are 3 instances of the character x. Another properties or characteristics of this things that we're doing is that we're trying to imagine the end goal of our function, kind of like how beginning with the end actually works. So we start with the end and then boil down the solution from there. Now let's first identify the subproblem. As in the previous example, we'll say the subproblem is the original string minus its first character. So for ax, bx, cxd, the subproblem is xb, xc, xd. So we remove the a, the first character again. Next, let's imagine count underscore x has already been implemented. If we call count underscore x on our subproblem, by calling count underscore x and then quotation x, bx, cxd, we get 3. To that, we just need to add 1 if our first character is also an x. So to that, we just need to add 1 if our first character is also an x. So we just need to create, in this case, an if-else statement. So if the first character is also an x, because that is related to the end goal that we want to achieve, therefore we will add 1. So if our first character is not an x, we don't need to add anything to the result of our subproblem. So here's our example function. So def count underscore x, so and then parameter string, if string index 0 equal x, or quote x, return 1 plus count x string, and then 1 comma string dot length minus 1, which is amazing, right? So else return count underscore x string 1 string dot length minus 1, end, and then end. So here we have a if else statement inside our function, which is essentially the same pattern with as before. We call that our recursive function inside the recursive function with the parameter inside the open and close parentheses, and then 1 starting from 1 comma string dot length minus 1. So this conditional statement is straightforward. If the first character is an x, we add 1 to the result of the subproblem. Otherwise, we return the result of our subproblem as is. Here too, we're basically done. All we need to do is deal with the base case. We can say that the base case here is when a string has only one character. So again, if it's string, the base case is if it's one character. And then if a number, the base is if it only have one number, because you cannot not go negative. But it still depends on your goal. But usually you don't create a recursive function for negative values. So, but this leads to some awkward code, since we really have two base cases, as the single character may be an x, but also may not be an x. So here, we define count underscore x with parameters string. So here's the base case. So ready? If string dot length equals to 1, so and then we create a nested if string index 0 equals to quote x, return 1, else return 0, and then end. So we have an if else statement with an if loop, and then end to close this if parent loop. Now we're gonna create the previous code we've done on our subproblem case, which is if string index 0 equals to quote x. So essentially these are actually inside that if parent, right? So we put that in the parent, but we also have this after that, whole parent code. So if string index 0 equals to x, return 1 plus count under x string 1 comma string dot length minus 1, else return count underscore x string 1 string dot length minus 1. So it's the same code as the one we did earlier. So essentially we have two parent codes here. But the second one, so notice the pattern again. The base case become the first set of code, and then if it's has a conditional, we're gonna create a separate parent code, and then after that we're gonna create the sub problem code that we just created. So thankfully we can simplify this using another simple trick. So in many language, calling string 1 comma 0 returns an empty string. With this in mind, we can actually write our code more simply. So def count underscore x with parameters string, the base case an empty string. So instead of a parent loop if and then if else inside, we just use this return 0 if string that length equals 0, and then we use the sub problem code, which is if string index 0 equals quote x, return 1 plus count underscore x string 1 dot string dot length minus 1, else return count underscore x string 1 comma string dot length minus 1 end. So in this new version version, we say that the base case occurs when the string is empty, string dot length equal 0. So the base case is when the string is actually empty. So this is the one-liner code we replace for the if parent code, which returns 0 of string dot length equal 0. Now in this new version, we say that the base case occurs when the string is empty, string dot length equal 0. So that's the base case. We return 0 because there will never be an x in an empty string, right? So since we know that there will never be an x in an empty string, we can use that instead of that creating if x, if the first character string is equals to x, we're gonna return 1. So here, since we know that at the end, that if it's 0, therefore there will never be an x. So return 0 if string dot length equal 0 is a great way to make as our base case and to minimize our code. When the string has just one character, the function will add 1 or 0 to the result of the next function call. So when the string has just one character, the function will add 1 or 0 to the result of the next function call. This next function call is count underscore x string 1 comma 0. Since string dot length minus 1 is 0, because the string 1 0 is an empty string, this final call is base case and returns 0. So when the string has just one character only, the function will add 1 or 0 to the result of the next function call. So for the record, calling array 1 comma 0 also returns an empty array in many languages. So we could have used the same trick in the previous two examples as well. So we can use this same trick as well in the previous what's that problem? Sum, I think. I forgot. Reversal string and sum, array sum. So we can also use this because for many languages, calling array with the first parameter 1 comma 0 also returns an empty string. So we could have used the same trick in the previous two examples as well. The staircase problem, you may still be skeptical and ask, why do we need this new mental strategy anyway? I've been able to solve these problems with loops just fine until now. Indeed, you may not need a new mental strategy for simpler computations. However, when it comes to more complex functions, you may find that recursive mindset makes the writing of code much easier. So in here, I think staircase. Now, we're not gonna use the combination of loops and recursion here. So in this staircase, let's say we have a staircase of n steps, and a person has the ability to climb 1, 2, or 3 steps at a time. How many different possible paths can someone take to reach the top? Write a function that will calculate this for n steps. So for n steps, depending on how far, like one step could be three stairs, or one step could be 2 stairs. So you need to write a function that will calculate this for n steps for any possible cases. Now the image displays 3 possible paths of jumping up a 5-step staircase. Now there are just 3 of many possible paths. So let's explore this problem with a bottom-up approach. That is, we'll work our way up from the simplest cases to the more complex ones. Obviously, if there's only one step, there's only one possible path. With 2 steps, there are 2 paths. So for 1 step, of course, there's only one path because you step through the staircase. With 2 steps, there are 2 paths. Like in this staircase, for example, you could jump from 0 to 2, and for 2 steps, and then after that the next step would be 3 steps, or 3 stairs rather. So with 2 steps, there are 2 paths. The person can climb 1 step twice, or the person can jump up 2 steps at once. So the person can climb 1 step twice. So 1 step for a person could mean twice. So the person can climb 1 step twice. So, or the person can jump up 2 steps at once. So we'll write this as 1 1 or 2. So we can make a 2 stairs as a 2 separate step, or you can make it a 1 step. So that's what it means. With the staircase of 3 steps, someone could take one of 4 possible paths. So if the staircase has a 3 steps, here's the different path that he could take. 1 stairs at a time, 1 stairs and then 2 stairs, or 2 stairs, or 1 stairs, or 3. So with 4 step, there are 7 options. So again, we're starting at the end here. We're looking what is the possible permutations that we can do, or edge cases that our function needs to meet. So go ahead and try to draw up all the combination for a 5 staircase. It's not that easy, and this is just 5 steps. Imagine how many combination there are for 11 steps. Now let's get to the question at hand. How would we write the code to count all the paths? Without the recursive mindset, it can be difficult to wrap one's mind around the algorithm for making this calculation. However, with the top-down way of thinking, the problem can become surprisingly easy. For an 11 steps staircase, the first problem that comes to mind is a 10-step staircase. So for an 11 step, the first sub-problem, of course, without the base case, which is 10-step case, 10-step staircase. Let's go with that for now. If we knew how many possible paths there are to climb a 10-step staircase, can we use that as a base case for calculating the paths for an 11-step staircase? So for starters, we do know that climbing an 11-step staircase will take at least as many steps as climbing a 10-step staircase. That is, we have all the paths to get to stair number 10, and from there, one can climb 1 more step to get to the top. However, this can't be the complete solution, since we know that someone can also jump to the top from stair numbers 9 and 8 as well. So if we think about it further, we'll realize that if you're taking any path that includes going from stair 10 to stair 11, you're not taking any of the paths that include jumping from stair 9 to stair 11. So if you're jumping from 10 to 11, of course you're not thinking about jumping from 9 to 11. Conversely, if you jump from stair 9 to stair 11, you're not taking any of the path that include stepping on stair 10 to 11. So we know that the number of paths to the top will include at least the number of paths to stair 10 plus the number of paths to stair 9, because those are the steps prior to step 11, 10, 9, 8, etc. And since it's possible to also jump from stair 8 to stair 11, as one can jump 3 steps at a time, we need to include the count of those paths as well. So we've determined then that the number of steps to the top is at least the sum of all the paths to stairs 10, 9, and 8. So yes, the number of steps from 8, 9, and 10 would be the number of steps to the top. However, in thinking about it even further, it's evident there aren't any other possible paths to the top beyond this. After all, one cannot jump from stair 7 to stair 11. So we can conclude that for n steps, the number of paths is number of paths n minus 1 plus number underscore of underscore paths n minus 2 plus number underscore of path n minus 3. So I'm guessing you recognize this pattern from the previous video. So other than the base case, this will be the code for our function. So we define number underscore of paths and then parameter with only one, which is n. So number underscore of underscore paths n minus 1 plus number underscore of paths n minus 2 plus number of underscore paths n minus 3, and then end. So it seems too good to be true that this is almost the code we need, but it is true. All that's left to deal with is the base case. So in this case, we actually just need number of steps n minus 1 up to until 3. So the staircase problem base case. So we already have the sub problem. Now we need to determine the base case. So determining the base case for this problem is slightly tricky. That's because when this function gets to an n of 3, 2, or 1, the function will call itself on n of 0 or below. For example, number underscore of underscore paths 2 call itself 4, number underscore of underscore paths 1, number underscore of underscore paths 0, and number underscore of underscore paths negative 1. One way we can deal with this is by hard coding all the bottom cases. So here is the revised function. Def number underscore of underscore paths parameter n, return 0 if n is less than equals to 0, return 1 if n is equals to 1, equals to 1, return 2 if n equals to 2, return 4 if n equals to 3 because we're adding that 1 plus 2 equals to 3. So plus we return 4 if n equals to 3. So return number underscore of underscore paths n minus 1 and then the permutation. So now those are the base case. Now we're gonna add the sub problem and then end. So another way to devise the base case here is to cleverly rig the system by using strange but effective base cases that just happen to compute the right numbers. Let me show you what I mean. We know that we definitely want the result of number underscore of underscore paths 1 to be 1. So we'll start with the base case of return 1 if n equals to 1. Now we know that we want number underscore of underscore paths 2 to return 2, but we don't have to create that base case explicitly. Instead, we can take advantage of the fact that number underscore of underscore paths 2 will compute as number underscore of underscore paths 1 plus number underscore of underscore paths 0 plus number underscore of underscore paths negative 1. Since number underscore of underscore paths 1 returns 1, if we made number underscore of underscore paths 0 also return 1, and number underscore of underscore paths negative 1 return 0, would end up with a sum of 2, which is what we want. So we can add the following base case. Return 0 if n is less than 0, return 1 if n is equals to 1, or n equals to 0. So let's move on onto the number of paths, which is 3, which will return the sum of number underscore of underscore paths 2 plus number underscore of underscore paths 1 plus number underscore of underscore paths 0. We know that we want the result to be 4, so let's see if the math works out. We already rigged number underscore of underscore paths 2 to return 2. Number underscore of underscore paths 1 will return 1, and number underscore of underscore paths 0 will also return 1. So we'd end up getting the sum of 4, which is just what we need. Our complete function can also be written as def number underscore of underscore paths parameter n, return 0 if n is less than 0, return 1 if n equals to 1 or n equals to 0, and then the sub problem code, which is return number underscore of underscore paths n minus 1 until n minus 3, and then end. So while this is less intuitive than our previous version, we cover all the base case with just 2 lines of code. So instead of returning up until 4, we just return 0 if n is less than or equal to 0, and then until return 4 if n equals to 3. We just use 2 lines of code. So we cover all the base cases with just 2 lines of code. As you can see, the top-down recursive approach made this problem much easier than it might have been otherwise. So an anagram generation. So to top off our conversation with writing recursive function, let's tackle our most complex recursive problem yet. We're going to use everything we've got in our recursion toolbox to make this work. So this is where we will combine the loops and recursive function. We're going to write a function that returns an array of all anagrams of a given string. So an anagram is reordering of all the characters within a string. So it's like all the possible combination of characters. So the anagrams of ABC are ABC, ACB, BAC, BC, AC, ABC, BA. Now let's say we were to collect all the anagrams of the string ABCD. So let's apply our top-down mindset to this problem. Presumably, we could say that the subproblem of ABCD is ABC. The question then is, if we had a working anagram function that returned all the anagrams of ABC, how can we use them to produce all the anagrams of ABCD? So we're gonna use the subproblem ABC to then compute all the anagrams of ABCD. Think about this for a bit and see if you can come up with any approaches. Here's the approach that occurred to me. There are others though. If we had all 6 anagrams of ABC, we can come up with every permutation of ABCD. If we stick the D in every possible spot with each anagram of ABC, here's what we can see. D and then ABC, D and ACB, D and BCA, D and BCA, D and BAC and D and BCA, D and CAB, and D and CBA. So here's a full Ruby implementation of this algorithm. You'll note that it's certainly more involved than the previous example in this chapter. So first, we define the anagrams underscore of, and then parameter string, and then we define the base case. If the string is only one character, return an array containing just a single character string. So return string index 0 if string.length equals to 1. And then create an array to hold all the anagrams. So collection equal open and close square bracket. Find all anagrams of the substring from the second character until the end. For example, if the string is ABCD, the substring is BCD. So we'll find all anagrams of BCD. So the first character is A. We'll find the subset problem of BCD. Substring anagrams equal anagrams of, again, string, and then the parameter of 1, comma, string.length minus 1, kind of like in the previous examples. And then iterate over each substring underscore anagrams that each do substring underscore anagrams. And then iterate over each index of the substring from 0 until 1 index past the end of the string. 0 dot substring underscore anagram dot length dot each do index. Then create a copy of the substring anagram. Copy equals to string dot new parameter substring underscore anagram. Then insert the first character of our string into the substring anagram copy. Insert the first character of our string into the substring anagram copy. So we insert the first character in our string into the substring anagram copy. Where it will go depends on the index we're up to within this loop. Then take the new string and add it to our collection of anagrams. Collection, copy that insert index, comma, string, index 0, and n. Return the entire collection of anagram. Return collection n. So this code is not trivial, so let's break it down. For now, we'll skip over the base case. We'll start by creating an empty array which will collect the entire collection of anagram, which is collection equals this open and close square bracket. So this is the same array we'll return at the end of our function. Next, we grab the array of all anagrams from the substring of our string. So we'll grab the array of all anagrams from the substring of our string. This substring is the problem, the subproblem string, namely from the second character until the end. For example, if the string is hello, the substring is ELLO. So substring underscore anagrams equals anagrams underscore of, then string 1 that length minus 1. So it's kind of like the sub problem that we create in the previous example without the index 0 or the first character or number. Note how we use the top-down mentality to assume that the anagrams of function already works on substring. We then iterate over each of the substring underscore anagram, substring underscore anagrams each do substring underscore anagram. So that's how we expect the function to work even without knowing its details. Before moving on, it's worth noting that at this point we're using a combination of loops and recursion together. So in this, like what I've said, we're using the combination of loops and recursion. Using recursion doesn't mean that you have to eliminate loops from your code altogether. We're using each tool in a way that most naturally help us solve the problem at hand. For each substring anagram, we iterate over all of its indexes. So if each of the substring of this anagram, we iterate of all of these indexes to make a copy of the substring anagram and insert the first character of our string, the only character not contained within the substring, into that index. Kind of like the base case. Each time we do this, we have created a new anagram, which we then add to our collection. So here, 0 dot dot, this is where the 0 dot dot substring underscore anagram dot length that each do with the parameter index copy equals the string dot new substring underscore anagram, and then we insert it to collection copy that insert index and then the string 0. So we copy that input index or the result of our anagram algorithm. When we're done, we return the collection of our anagrams. The base case is where the substring only contains only one character, in which case there's only one anagram, so the character itself. So the base case is string 0. The purpose of this is that, let's say there's only one anagram, you only put one. Of course, there's no permutation or combination of that. So as an aside, let's stop for a moment. So that's the reason also why we have here for inserting collection, copy that insert parameter index comma string index 0, because that's index 0 will serve as our base case. As an aside, let's stop for a moment to analyze the efficiency of our anagram generating algorithm, since we'll discover something interesting. In fact, the time complexity of generating an anagram is a new category of big O that we haven't encountered before. If we think about how many anagrams we generate, we'll notice an interesting pattern. For a string containing 3 characters, we create permutation that start with each of the 3 characters. So for a string containing 3, we create a permutation that starts with each of the 3 characters. Each permutation then picks its middle character from one of the 2 remaining characters and its last character from the 1. It's kind of like the factorial. So here is the graph. This is 3 times 2 times 1, which is 6 permutations. Looking at these first string lengths, we get for 4 characters, 4 times 3 times 2 times 1 anagrams, 5 characters, 5 times 4 times 3 times 2 times 1, which is another way of saying factorial. Remember that big O expresses the answer to the key question. If there are n data elements, how many steps will the algorithm take? In our case, n would be the length of the string. For a string of length n, we produce n factorial anagrams. In big O notation then, this is expressed as O n exclamation. This is also known as factorial time. O n factorial is the slowest category of big O will encounter in this course. Although O n factorial is extremely slow, we don't have a better option here, since our task is to generate all the anagrams, and there simply are n factorial anagrams for an n character word. In any case, recursion played a pivotal role in this algorithm. which is an important example of how recursion can be used to solve complex problem. So in any case, recursion played a pivotal role in this algorithm, which is an important example of how recursion can be used to solve complex problem. So here, recursion including loop are pivotal role to solve this anagram problem. So we use an anagram algorithm, but it's slow, but it's all that we can do. Now we'll discuss dynamic programming. So while recursion can certainly solve some problems, it can also create new ones if not used properly. And in fact, recursion is often the culprit behind some of the slowest categories of big O, such as O2 raised to n. So it's not just factorial that it generates, though we found that in anagram generation example, but anagram generation is not the only algorithm that recursive function could create. So in some cases, it produced 2 raised to n. So unnecessary recursive calls, which is, by the way, 2 raised to n is faster than factorial. Unnecessary recursive calls. So here's a recursive function that finds the greatest number from an array. So there's a lot of problem for this that which make it slower or code slower, which we're gonna discuss. First is unnecessary recursive call. So here's a recursive function that finds the greatest number of an array. Let's make it bigger. We define max function and then a parameter array. Base case, if the array has only one element, it is by definition the greatest number. Kind of like in anagram, if we have a one character, of course we have permutations. We don't have any other permutations of that because it's only one character. Return array index 0 if array dot length equal 1, and then compare the first element with the greatest element from the remainder of the array. If the first element is greater, return it as the greater number. So here's the code for that. If array index 0, which is the first element, is greater than max array with a parameter 1 comma array dot length minus 1 again this is what we are using in a sub problem. Return array index 0 because we're trying to find the greatest number from an array. Otherwise, return the greatest number from the remainder of the array, else return max array 1 dot array length minus 1. So as you can see, it's the same sub problem that we use, or the same code for the sub problem. In this case, we just didn't add the first index because this algorithm are trying to find the maximum number from an array. In this case, or the first case, is that we return array index 0 if array dot length equals to 1. That is if it's only one element. We also cover the edge case that if the array first index is greater, or in the code, if array index 0 max array 1 comma array dot length minus 1, we return the index 0. So it's kind of like these two are the base case. So if it's 0, we'll handle that case, or the if we return array index 0 if array dot length is equals to 1 only, if only have one character in the array. So here the essence of each recursive call is the comparison of a single number array 0 to the maximum number from the remainder of the array. To calculate the number from the remainder of the array, we call the very max function we're in, which is what makes the function recursive. So we call the same function that we're in, which makes the function recursive. We achieve the comparison with the conditional statement. The first half of the conditional statement is if array index 0 greater than max array 1 comma array dot length minus 1, return array index 0. The snippet says that a single number array 0 is greater than what has already been determined to be the maximum number of the rest of the array. Max array with the parameter 1 comma array dot length minus 1. Then by definition, array index 0 must be the greatest number. So we return it. The second half of the conditional statement is else return max array 1, comma array that length minus 1. So again, let's go back. So this snippet, for the first snippet, says that if the single number array index 0 is greater than what has already been determined to be the maximum number of the rest of the array, so we need to determine first what is the max of the array without the base case, which is the index 0. Then by definition, array 0 must be the greatest number, so we return the array 0 since we're finding the maximum number in the array. The second half of the conditional statement is else return max array 1, comma array that length minus 1. Otherwise, we're gonna return the maximum number for the subset code, subset problem code, like in the previous example. So this second snippet say that if array index 0 is not greater than the greatest number from the rest of the array, then the greatest number from the rest of the array must be the greatest number overall, and we returned it. While this code works, it contains a hidden inefficiency. If you look carefully, you'll note that our code contains the phrase max array 1, comma array length that minus 1 twice, one in each half of the conditional statement. So the problem with this is that each time we mention max array 1 that array length 1 minus 1, we trigger an entire avalanche of recursive calls. So let's break this down for an example of array 1, 2, 3, 4. We know that we're going to start by comparing the 1 with the maximum number of the remaining array 2, 3, 4. That in turn will compare 2 against the max of the remaining 3, 4, which in turn will compare 3 against the 4. This 2 triggers one more recursive call on the 4 itself, which is the base case. However, to really see how our code plays out, we're going to start by analyzing the bottom call and working our way up the call chain. So we're gonna start on the bottom to really see how that twice call of that recursion is actually slowing our code. So when we call max 4, the function simply returns the 4. So let's say we call the max 4 at the bottom. The function simply returns the number 4. Again, this is because our base case is when the array only contains one element as dictated by the following line of code, or the first code that we wrote. Return array index 0 if array that length equal 1, since we only have one. This is straight forward. It's a single function call. Moving up the call chain, let's see what happens then when we call max 3, 4. In the first half of the conditional statement, if array index 0 is greater than max array 1, comma array that length minus 1, we compare the 3 to the max 4. But calling max 4 itself is a recursive call. The following diagram depicts max 3, comma 4 calling max 4. So here we have max 3 and 4 and then calling max 4. Now that next to the arrow, we put the limit first to indicate that this recursive call was triggered by the first half of the conditional statement within max 3, 4. After this step has been completed, our code can now compare the 3 with the result of max 4. Since we already calculated the 3, 4, we can compare now the 3 with the result of max 4 as shown in the diagram. Since the 3 is not greater than the result 4, we trigger the second half of the conditional statement. This is the code return max array 1, comma array that length minus 1. In this case, we return max 4. But when our code returns max 4, it triggers the actual function call of max 4. This is now the second time we triggered the max 4 call. So we triggered a necessary call. As you can see, As you can see, the function max 3, 4 ends up calling max 4 twice. Of course, we'd rather try to avoid this if we don't have to. If we've already computed the result of max 4 once, why should we call the same function again just to get the same result? However, this problem gets a lot worse when we move just one level up the call chain. Here's what happens when we call max 2, 3, 4. During the first half of the conditional, we compare the 2 against max 3, 4, which we've already determined look like this. So max 3 4, and then max 4, we could call max 4 twice for this, since the 4 is the greatest value when it's only have 4 number, and for 3 and 4 combination, 4 is still the max number. So for max 2 3 4, calling max 3 4 then would look like this. First max 2 3 4 for the first level, and then max 3 4 for the second level, and then for the third level max 4, and then max 4 again. But here's the kicker, this is just for the first half of the conditional max 2 3 4. For the second half of the conditional, we'd end up calling max 3 4 again. So for the first level, max 2 3 4, first level of the 3, second level max 3 4, and then max 3 4. For the third level, max 4 max 4 max 4 max 4. So we called max 4 4 times. That's there to move to the top of the call chain, calling max 1 2 3 4. When all said is done, and we after we call max for both halves of the conditional, we get what is shown in the diagram. So first level max 1 2 3 4, second level max 2 3 4, max 2 3 4, 2 max 2 3 4, and then third level max 3 4, then max 3 4, and then max 3 4, and then max 3 4. For the fourth level, we have max 4 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 max 4. So essentially 2 max 4 in each parent element or level. So when we call max 1 2 3 4, we actually end up triggering the max function 15 times. We can see this visually by adding the statement puts recursion to the beginning of our function. So it's kind of like the call lag. So remaining code omitted. So when we run our code, we'll see the word recursion printed to our terminal 15 times. Now we do need some of those calls, but not all of them. We need to calculate max 4, for example, but one such function call is enough to get the computed result. But here we call the function 8 times. So we're gonna continue this with little Vix for big O. Efficiency of recursion, overlapping subproblems, dynamic programming through memoization, implementing memoization, dynamic programming through going bottom up, memoization versus bottom up. So